I am happy to let you know organic grains processing. Learn milling and blending naturally gluten-free organic grains on EGG, millet, buckwheat. I will provide the detailed guide, focusing on the critical temperature and moisture control points. Critical control points guide. Temperature and moisture management. In the processing of organic, naturally gluten-free grains like millet and buckwheat, controlling temperature and moisture content is paramount. These two factors directly influence product quality, nutritional integrity, especially for organic claims, safety, preventing mold, pathogens, and shelf stability. Here is a comprehensive guide to the critical monitoring points across the 5 processing phases. 1. Phase 1. Sourcing and receiving control. The moisture level of incoming grain is a primary determinant of storage safety and milling performance. A. Moisture content receiving specification. The single most important measurement at receiving is the raw grain's moisture content. Target range. Incoming raw millet and buckwheat must typically be within a safe moisture range of 10% to 14%. The exact upper limit is set by the facility based on local climate and intended storage time. High moisture risk. Grain received with a moisture content above 14% poses a severe risk of mold growth. G. Aspergillus or Penicillium species, and the subsequent production of mycotoxins. G. Aflatoxin. It also leads to accelerated respiration, which generates heat, potentially reducing the grain's viability and quality. Measurement protocol. The moisture content must be measured immediately upon receipt using a calibrated grain moisture meter, e.g. electrical resistance or dielectric constant type. This reading should be logged on the incoming lot record, receiving log. Acceptance rejection criteria. Any batch exceeding the maximum acceptable moisture level, 14%, must be immediately segregated or rejected, as high moisture compromises both the safety and long-term organic quality of the product. B. Storage temperature and monitoring. Goal: to maintain the grain's dormancy and minimize pest activity. Target temperature. Raw grain should be stored in silos or bulk bags at temperatures below 15 degrees Celsius to 20 degrees Celsius. Cooler temperatures significantly slow down biological activity, insects, mold, respiration. Monitoring. Use a thermocouple system or similar sensors embedded within the storage structure to track temperature profiles daily. Unexplained localized heat spikes, 5%, indicate microbial or insect activity requiring immediate action, e.g. aeration, turning the grain. 2. Phase 2. Cleaning and preparation controls. Controlling temperature during cleaning is crucial, particularly during the dehulling step, to maintain organic nutritional integrity. A. Dehulling temperature control. Millet and buckwheat dehulling. The dehulling process involves mechanical impact, friction, which naturally generates heat. Excessive heat can cause lipid oxidation in the groat, leading to rancidity, and can potentially degrade sensitive vitamins, compromising the grain's organic quality. Maximum temperature limit. The temperature of the grain must be continuously monitored as it exits the dehuller. A typical limit is to keep the groat temperature below 40 degrees Celsius. Exceeding this limit for prolonged periods indicates excessive friction. Control method. Air cooling systems or adjusting the dehuller feed rate and clearance are used to manage friction and heat output. B. Tempering conditioning, if applicable. While less common for buckwheat and millet than for wheat, sometimes grains are lightly conditioned, adding moisture before specific milling to optimize bran removal. Moisture goal. If conditioning is performed, the moisture addition must be precisely controlled, e.g. increasing moisture by 0.5% to 1%, and the grain must be allowed to temper for a controlled time, e.g. 6 to 12 hours, to allow the moisture to migrate uniformly, and this time and temperature must be logged. Phase 3. Milling process controls the highest heat risk. Milling is the phase where friction is maximized, presenting the greatest risk of heat-induced degradation. A. Milling temperature monitoring. Heat generation. Both stone mills and roller mills generate significant heat. In stone milling, high heat can damage the entire grain structure. In roller milling, excessive heat can reduce the flour's baking quality, though less critical for GF flours. Crucially, high heat can lead to the loss of volatile compounds and B vitamins, impacting the product's nutritional profile and organic quality claims. Maximum temperature limit. The temperature of the milled flour must be continuously monitored at the point of discharge. Target limits are often set between 35 degrees Celsius and 45 degrees Celsius. Control methods. Air-cooled mills, utilizing chilled air injection into the mill housing. Mill load, reducing the grain feed rate to lower friction. Post-milling cooling, immediately passing the hot flour through a fluidized bed cooler or air cooling system before sifting and storage. B. Moisture content after milling. Flour moisture goal. The final milled flour moisture is critical for shelf stability. It must be consistently at or below the desired safe storage level, typically 12% to 13%. Logging. A sample must be tested for moisture immediately after sifting and the result logged against the production batch record. Excessively dry flour below 10% can lead to static buildup and dusting issues. Phase 4. Blending and formulation controls. Moisture control at this stage prevents clumping and maintains the functional stability of the final blend. A. Ingredient moisture verification. Incoming inspection. Before blending, all secondary ingredients, e.g. rice flour, starches, gums, must be checked to ensure their moisture content is within specification, usually 12%. Introducing high moisture ingredients compromises the entire blend. B. Blending temperature control. Friction. The friction created within the industrial ribbon blender can also generate heat, particularly during long blending cycles. This can cause the blend components, especially the gums, hydrocolloids, to hydrate prematurely or clump. Monitoring. The temperature within the blender should be checked periodically to ensure it stays close to ambient room temperature, typically below 30 degrees Celsius. C. Final blend moisture specification. Finished product. Moisture. The final mixed blend must be tested and logged. The accepted moisture level is usually tighter than the raw grain, often specified at 12.5% maximum, to guarantee resistance against microbial activity during storage and transit. Phase 5. Packaging and storage controls. Maintaining control ensures product stability until it reaches the consumer. A. Packaging environment control. Relative humidity, RH. The packing room air must be controlled, ideally maintaining relative humidity below 60%. High RH can lead to the finished flour absorbing moisture from the air, increasing its risk of caking and mold growth. B. Finished goods storage. Temperature. Store the packaged organic GF flour in a cool, dry warehouse environment, maintaining temperatures similar to or cooler than the raw grain storage, below 20 degrees Celsius. Moisture migration. Storing finished flour bags directly on the floor or against an exterior wall should be strictly avoided, as this can cause temperature fluctuations and localized moisture migration, condensation, which initiates spoilage. Pallets must be used. By establishing strict maximum and minimum values for both temperature and moisture at each of these 5 critical steps, the facility ensures the final millet and buckwheat blend is safe, retains its nutritional profile, and complies with both organic and gluten-free standards. Thank you for watching. Please subscribe my channel and help grow the channel.